So this is the third of the 3 videos on line integrals, where we are now going to reap the rewards of the first 2 videos. The first video, just as a reminder, we found a test for when a vector field was conservative, and in the second video we established how to find the scalar potential function of that vector field, the conservative vector field, and now we get our reward, because basically what there is a fundamental theorem of calculus for line integrals where the vector field is conservative and there is a scalar potential function. Okay, so basically let's just go through the theory, and then what we're going to do is go through an example that we've already done in a video. The description to all of these videos and the links is in the description to this video. But anyway, so basically in traditional integration of one dimension, we have the definite integral, the integral between a and b of f dash x dx is fb minus fa, where the value of the integral depends only on the initial and final points a and b. Okay, and what we're looking for is a version of that works for vector line integrals. Okay, so basically here for line integrals we have a version of this, right? Okay, so if C is a curve defined by this, where t goes between a and b, and f x y z is a scalar, well, it's a function, but it's a scalar potential function whose gradient vector, the grad of f x y z, is continuous, then we have this, which basically says that the integral of the gradient of f dot product with dr is equal to the function at its value at r of b minus the function and value at r of a. Basically, it is only dependent on the endpoint and the initial point. Okay, now another way of writing this, and we've already done this in previous videos, is that obviously the gradient of f x y z is the vector field, the conservative vector field f x y z. And another way of writing this, and again we've done this in previous videos, is that f x y z can be written as f1 dx at f2 dy at f3 dz. All of these, if the vector field is conservative, basically evaluate to the scalar potential function at r of b minus r of a. Okay, now to put it another way, the integral is independent of path, i.e. it's only dependent on the initial and final point. And as such, the final thing is that if we went round a circle, for example, like that, where our starting point and end point were both the same, then by definition, as we go round that circle, if our value is only dependent on the end point value minus the beginning point value, if they're the same point, then clearly the integral there must be 0, as long as the path C is a simple closed path. Okay, so what we're going to do now is let's just put that into action. Now go into this question here, which we've already done a video on, and again the link is in the description. So we've got to compute the line integral over C of yz dx add xz dy add xy dz along this curve C, and we did this 2 ways in the previous video and we got the answer to be 64. Now what we're going to do is we're going to do it 2 more ways here. The first way we're going to do is we are going to use the fundamental theorem of calculus for line integrals, and then what we're going to do is we are going to choose a different path to go down and see if we still get the same answer, which we must do according to the fundamental theorem of line integrals if this is a conservative vector field. So the first thing we've got to do is check that it's a conservative vector field, and to do that we have to check that df1 dy equals df2 dx, and again we've done this in a previous video, so if you're not clear on what we're doing here, just have a look at the playlist line integrals, and we explain what all of this means. df3 dx and df2 dz equals df3 dy, where this here is f1 and this here is f2 and this here is f3. Now fortunately it's relatively easy to do these differentials, so we can do them basically here. Now df1 dy there basically is equal to z, and that's got to equal df2 dx. There's df2 dx, well that's equal to z, so that's correct. df1 dz is equal to y, and df3 dx is equal to y, so therefore that's correct. And df2 dz is equal to x, and df3 dy is equal to x, x. So that's correct, so therefore good. All of this counts, so the test for whether it's a conservative vector field is correct. So we know that it's a conservative vector field. That was the test we did in the first video. Now what we need to do is find what the potential function is. So let's do that. And again, we've already done how to do this in the second video of the 3. So we know that df dx, where f is our potential function, is yz. We get that from here. And we know, I need a bit more space here, df dy is xz, which we get from here. And we know that df dz is equal to xy, which we get from here. So basically, per our previous video, what we have to do is we have to integrate this with respect to x, and that gives us f equals xyz plus some function of y and z. And then what we do is we differentiate this with respect to y, and df dy gives us xz add d dy of g of y of z, and then we compare this to this. Well, clearly that means that dg of y and z dy equals 0. Therefore, g is equal to a function of z only. So therefore we know that f equals x, y, z add some function h of x from there. And now what we do is we differentiate that with respect to z, and that gives us xy add d, sorry, that should be a z there, d dz of h of z, and we compare that to this here, and therefore clearly d dz of h of z is 0, and therefore h of z is some constant of integration, and therefore we know that f, our scalar potential function f, is equal to xy z add some constant of integration. And so we have our scalar potential function here. Okay, so now by the fundamental theorem of calculus for line integrals, we are going to use this one here. Basically, we have our f1. All we need to do now is input r of b and r of a on our scalar potential function. Okay, well, let's have a look. Looking at r of b, if we just get a bit of space here, sorry. So when t equals 0, our initial point will be putting 0 into there, will be 0, 0, 0. And our end point will be putting 2 into there, which will be 2, 4, 8. So that's our initial point and our end point. Okay, so by the fundamental theorem of calculus here now, we know that the integral of, what was the integral again? Let's write it down, yz dx add xz dy add, what was the other one? xy dz. We know that that integral equals, by the fundamental theorem of calculus for line integrals, we know that that equals f of r of b minus f of r of a. And we've just established what r of b and r of a are, and we know what f is because we just worked it out here, which equals x, y, z between the point 2, 4, 8 and 0, 0, 0 by the fundamental theorem of calculus for line integrals, which equals 2 times 4 times 8, which is 8 times 8, which is 64. Hurrah! We have the same answer by the fundamental theorem of calculus for this line integral as we did in the video where we worked it out the other way. Okay, so now let's do another thing then. Let's, instead of going along the curve t squared t cubed from t equals 0 to let's go along a different curve. So the curve that we have just gone along was basically something that looked something like that, for going from the point 0, 0, 0 to 2, 4, 8, and that was basically parameterized as t squared t cubed. Well, the fundamental theorem of calculus for line integrals says it doesn't matter what the path is, it only depends on our end point and beginning point. So let's test that. Why not just do it as the line segment here, going from 0, 0, 0 to 2, 4, 8. Okay, so what we'd have to do is we have to parameterize that line segment. Okay, well, the line segment from 0, 0, 0 to 2, 4, 8, the line segment would be parameterized as 2t, 4t, 8t from t greater than or equal to 0 and less than or equal to 1. That's that line segment there, parameterized. Okay, so now what we've got to do is we will integrate yz dx, add xz dy, add xy dz. We're going to integrate that along the curve, this new curve, the line segment now. Okay, so basically we're going to use x is 2t and y is 4t and z is 8t instead of t squared and t cubed, which was the curvy curve. And so therefore we have dx equals 2 dt, dy equals 4 dt, and dz equals 8 dt. So we can now plug all of this into here, and that gives us the integral from t equals 0 to 1 of, okay, well, yz is 4t times 8t times dx, which is 2 dt, add xz is 2t times 8t times dy, which is 4 dt, add xy, which is 2t times 4t times dz, which is 8 dt, which equals, give us a bit more space here, so basically that equals the integral between t equals 0 and 1. And remember, this bet had give us 64, otherwise we're in trouble. Basically 4 times 2 is 8 times that, 64 t squared dt, add, again, 64 t squared dt, add 64 t squared dt, and that gives us equals 3 times 64 times the integral between t equals 0 and 1 of t squared dt, which equals 3 times 64 times by t cubed over 3 between 1 and 0, which is 3 times 64 times a third, which is 64. And hey presto, even using a different curve, which was the straight line between the 2 points as opposed to the curved line, we still get the answer 64, which we have to do because the fundamental theorem of calculus for line integrals for conservative vector fields says that it is independent of the path and it's only dependent on the end point and the beginning point. Okay, well, I hope you've enjoyed this and you've enjoyed these 3 videos. If you have, please press the little thumbs up button and subscribe to the Gresty Academy YouTube channel. Thank you.